So our last lecture for section 6.5 and for chapter 6 in general, very short, just 3 slides on intermolecular forces. So there's 2 types of forces, intramolecular, and those would be your bonds. Those would be covalent, ionic, and metallic. Those are what holds the molecule together or the substance together within, okay, the molecule. Now, intermolecular forces are specifically between molecules. These forces are weaker than intramolecular forces. Bonding forces are much stronger than these intermolecular forces. So there's 3 different types that you're going to be responsible for. And the first type is dipole-dipole force. So this is a force of attraction that holds together polar molecules. Okay, like I said, they're weaker than bonding forces like covalent or ionic or metallic. Um, they do vary in strength. Molecules that are very polar tend to hold together better than molecules that are slightly polar. So that's a force of attraction that allows these molecules to sort of stick together, even though it's pretty weak. So down here, just our example diagram, you have, let me get to my laser pointer. Okay. We have these HCl's. Now, between the H and the Cl, that's a covalent bond. That's a bonding force. That's much stronger than an intermolecular force. But HCl is polar. It has a sort of partially negative end. Remember that symbol means partially, and a partial positive end. So 2 HCl molecules, and this is even showing 3, the partially negative end is attracted to the partially positive end. In this specifically, this force of attraction right here, still electrostatic, Coulomb's law, is a dipole-dipole force. Okay, when this molecule would be liquefied if it was frozen, or if it went to a vapor, that's what would be broken. You're not breaking up the H and the Cl into H2 and Cl2. You're just breaking up HCl and HCl. Okay, so that's a dipole-dipole force. So whenever you have a polar molecule, it's going to be held together with dipole-dipole forces. Okay. Now, there's a special type of dipole-dipole force that occurs between hydrogen and nitrogen, oxygen, or fluorine, and it's called hydrogen bonding. And I know we name it bonding. It's still not as strong as an intramolecular force or a bonding force, like this bond between O and H. But this bond between this O on one molecule and this H on a nearby molecule is extremely strong. This is one of our strongest intermolecular forces that we have. But it's very specific in what it is. As you can see up here, the intermolecular force in which a hydrogen atom that is bonded to a highly electronegative atom, so that would be like this hydrogen that's bonded to oxygen, which is very highly electronegative, is attracted to an unshared pair of electrons on an N, O, or F, nitrogen, oxygen, or fluorine atom on a nearby molecule. Okay, these 3 elements got pulled out as separate because the experimental data showed that with these 3, this bond was so much stronger than just a normal dipole-dipole force. Okay, so that's where hydrogen bonding got its name. And by far, the most common representation or exemplar of hydrogen bonding is water. That's why water has such a high melting point, why it has such a high boiling point, is because molecule to molecule, it's held together with this extremely strong bond. So when ice melts, you're not breaking the hydrogen to oxygen covalent bond, you're breaking the bond between one water molecule to a nearby water molecule. When water boils, you're totally separating water molecule to water molecule. So you're breaking that hydrogen bond. That's why it takes so much energy and so much time to boil water. There's a lot of energy that has to go into breaking this hydrogen bond. Okay? And lastly, our last type. Now, these London dispersion forces, named after Fritz London, these are the only intermolecular forces acting on nonpolar molecules and noble gases. They're by far the weakest of the intermolecular forces. Most nonpolar molecules and noble gases at room temperature are gases because they don't hold together very well. They just separate from one another. So these London dispersion forces, they're really in all molecules, even polar ones as well, but they're just so weak they're not as recognized as a dipole-dipole or a hydrogen bond. The intermolecular attraction resulting from the constant motion of electrons and the creation of instantaneous and induced dipoles. So when you think of dipole, that's just a separation of charge. You have a negative side, you have a positive side. So here's helium, for example. Helium is a noble gas. It has 2 protons, 2 neutrons, and then 2 electrons in its outer energy level, which is the 1s, which is the first energy level as well. What can happen, and you can see here, as these electrons are randomly moving around the atom, you can see here that we have 2 on one side. So there's sort of more negative charge over here than there is over here. So this is what's called an instantaneous dipole. It just occurs. Now, what it does in this nearby helium atom is because the negative side's over here, it repels these electrons. And let me kind of draw this on here. Let me get our pen. It kind of pushes these electrons over this way. So it causes this to form a dipole when it wasn't there, and that's called an induced dipole. Okay? So then what you get are uneven electron clouds. So over here, we have sort of a negative side, and over here, we have sort of a positive side. There's our partial positives and negatives. So it's attracted over here to this partial negative and this partial positive. Okay, so here's the force of attraction right in here. Okay, right in there. This is that London dispersion force. It just happens to occur because this helium atom became polarized instantaneously and caused this nearby one to be induced to become polar, and then they form that attraction. But as the electrons sort of move back or they move past each other, this force dies out and then they go back to their nice, normal, neutral, nonpolar cells. Okay, so those are your 3 intermolecular forces. Dipole, dipole, that's between polar molecules. Hydrogen bonding is very specific between hydrogen and an atom of N or F in a nearby molecule. And then finally, your London dispersion forces. They are the weakest of the intermolecular forces and the only ones really occurring with noble gases and non-polar molecules. Okay, so that's it for chapter 6, section 6.5. Yeah, on to chapter 7.